A single bismuth crystal grows along exactly 4 geometric axes simultaneously, and if you were scaled down to the size of an atom watching it happen, the lattice walls closing in would tear you apart at the molecular level before you even registered the danger. That's not a metaphor. That's crystallography. And once you understand why bismuth does this, why it builds itself like a haunted staircase that follows rules older than life itself, you will never look at a solid object the same way again. Let's start with something that seems obvious. Solid matter looks smooth. A metal cube looks like a cube. But zoom in far enough and every solid you've ever touched is actually a three-dimensional repeating grid of atoms, locked into a geometry that was decided the instant the material started cooling. The shape isn't decoration. The shape is physics made visible. Bismuth breaks that intuition open in the most dramatic way possible. When bismuth melts, and it melts at a surprisingly low 471 degrees Fahrenheit, which is barely above the temperature of a kitchen oven on maximum heat, something extraordinary begins the moment it starts to cool. The atoms don't settle randomly. They don't pile up like sand. They begin negotiating. Every single bismuth atom has a specific quantum mechanical preference for how it bonds to its neighbors. It wants angles. It wants distances. It wants geometry. And the geometry it wants is called a rhombohedral lattice, a structure where each atom sits at the corner of a slightly squashed cube, tilted 3 degrees off true. 3 degrees. That tiny tilt is the reason bismuth looks the way it does. Here's the analogy that makes it click. Imagine you're tiling a bathroom floor. You want perfect squares, edge to edge. But the tiles you were given are ever so slightly off square. You can force them into a rectangular grid, but they'll always resist. They'll always want to slide diagonally. That internal tension forces a compromise, and the compromise expresses itself as steps. As ledges. As terraced geometry spiraling outward from a central point. That's what bismuth does. That 3-degree tilt in its bonding preference means the crystal can't grow flat. It grows in hopper formation, a term from mineralogy that means the edges and corners solidify faster than the faces. Why? Because corners and edges have more exposure. They're touching more liquid bismuth. They grab atoms faster. The face of the crystal lags behind. So instead of a solid cube, you get a hollow, stair-stepping frame. Each layer slightly smaller than the one below it, descending inward like an architectural drawing of infinity. And here's where it gets stranger. The colors you see on a bismuth crystal, that iridescent rainbow of gold, purple, blue, green, those aren't pigments. There's no dye, no paint. What you're seeing is a layer of bismuth oxide that forms on the surface the moment the crystal hits air. That layer is only a few hundred nanometers thick. And because light waves bounce off both the top and bottom of that layer simultaneously, they interfere with each other. Different thicknesses cancel out different wavelengths. The color you see is literally determined by the exact nanometer thickness of an invisible film. Move the crystal 1 millimeter and the geometry changes. The color changes. The physics changes. If this is blowing your mind, subscribe right now. We do this every week. The science that textbooks either skip or bury under equations until it stops feeling real. Now here's the second layer. The part that reframes everything you just learned. Bismuth is diamagnetic. Not a little. Bismuth is the most strongly diamagnetic element that occurs naturally at room temperature. Diamagnetism means its electrons, when exposed to a magnetic field, generate their own opposing magnetic field. Bismuth pushes back. Place a powerful rare earth magnet near a bismuth crystal and the crystal will actually levitate, or more precisely, it will be repelled just enough to float above a properly arranged magnetic field. You can build a levitation rig from bismuth and 2 neodymium magnets and watch a physical object hover in mid-air through nothing but the geometry of its electron clouds. Think about that. The same 3-degree lattice tilt that makes it grow in staircases also controls how its electrons behave under a magnetic field. The macro-scale shape and the quantum-scale behavior are both expressions of the same underlying crystal geometry. The crystal isn't just visually interesting. It's a physical demonstration that quantum rules and large-scale structure are the same conversation, happening at different volumes. That connection, structure driving both aesthetics and quantum behavior, is exactly what materials scientists are trying to engineer deliberately in next-generation electronics. Topological insulators. Quantum computing substrates. Bismuth compounds are being studied right now as candidates for both, because the surface of a bismuth crystal conducts electricity in ways the interior does not. Electrons on the surface are protected by the topology of the crystal structure itself. They can't scatter. They travel without resistance along the geometric edges, the exact edges that grew fastest because they were most exposed to liquid metal during cooling. The staircase isn't random. The staircase is a circuit. And here's the implication that should keep you up at night. Every time you grow a bismuth crystal, every time anyone has ever grown one, they've been watching quantum mechanics write its own architecture in real time. The universe has preferences. It has favorite angles and forbidden distances. When matter is allowed to do whatever it wants with no interference, it builds staircases. It builds rainbows from invisible films. It builds circuits from geometry. We didn't design that. We just learned to read it. The next time you see a bismuth crystal in a science shop or a museum display, understand what you're actually looking at. You're looking at the moment physics decided what shape it wanted to be. You're looking at negotiation between atoms, made permanent in metal. You're looking at quantum rules expressed at the scale of something you can hold in your hand. That's what solids actually are. That's what matter is doing when nobody's watching. If that reframed how you think about physical reality, subscribe and hit the bell. Next video, we're going into why snowflakes and neural networks follow the exact same branching mathematics, and what that means for how the universe builds complexity.